This is the pocket cube, 2 by 2 by 2, the little sibling of the Rubik's cube. 8 corner pieces, 6 colored faces, and over 3.5 million ways to scramble it. And this is something else entirely. 4 curved lobes, welded together along glowing seams, floating in a haze of heat. No stickers, no plastic, nothing to solve, or so it seems. Because here is the claim of this video. These two objects are, in a precise mathematical sense, the very same machine. Every move you can make on the cube has a perfect twin move on this shape. Same moves, same rules, same algebra, 2 different bodies. Let's start with the toy. When you turn a face of the pocket cube, you're doing something surprisingly structured. Each quarter turn is a move. You can follow one move with another. Mathematicians call that composition. Every move can be undone. That's an inverse. And doing nothing at all counts as a move too. The identity. A collection of moves with those properties is called a group. The pocket cube group contains every rearrangement you can reach. All 3,674,160 of them, woven together by just a handful of quarter turns. But here's the key idea, and it's the heart of this whole story. The group is not the plastic, it's not the stickers. A group is the pattern of the moves themselves, and a pattern is free to live in more than one body. So meet the second body. This object is built from 4 curved lobes. Think of them as petals or spindles, glued edge to edge along a network of bright seams. The surface is smooth almost everywhere, bulging like a soap film, except along those seams where the lobes meet at crisp creases. Now watch the seams alone. Traced out, they form the skeleton of an octahedron. 6 junctions, 12 edges. And the octahedron is no stranger. It is the cube's dual. Its mirror twin. Put a dot at the center of each face of a cube, connect neighboring dots, and an octahedron appears. 6 faces on the cube, 6 seam junctions on the seed. That is not a coincidence. That is the wiring diagram they share. So, where's the puzzle? Watch closely. On the cube, a quarter turn slices the puzzle in half and rotates one half by 90 degrees. Here, the very same thing happens. The object splits cleanly along its seams. One half swings around, a rigid, perfect rotation, and then the pieces land exactly back on the seam network, as if nothing had ever been cut. This kind of motion is called a piecewise isometry. Every piece moves rigidly, no stretching, no bending, no tearing, and the seams are the only places where cutting is allowed. Put them side by side, and the dictionary writes itself. Turn a face of the cube. 4 corner pieces glide around the turning axis. Perform the twin move on the seed. The surface swings around the matching seam junction and lands back on itself perfectly. One move on the left, one motion on the right. Do them in sequence, and the sequences match step for step. Undo a move on the cube, and the seed's motion runs in reverse. That perfect matching has a name. When 2 systems have a one-to-one dictionary between their moves, where combining moves on one side always agrees with combining the translated moves on the other, mathematicians say the systems are isomorphic. Same shape, in Greek, not similar, not analogous, structurally identical. The pocket cube group and the seed's group of seam-respecting motions are one and the same group, wearing 2 costumes. Everything you know about one transfers instantly to the other. Every solving algorithm, every scramble, every clever trick, each has a twin on the seed, guaranteed. So why should you care that a toy and a curved blob share their algebra? Because the seed is not just a costume, it is a genuine geometric object. Heat can flow across its surface. It can vibrate like a drum. It has a spectrum of pure tones, and when you study those tones, the cube symmetry hiding inside starts talking to some surprisingly deep mathematics. That's a story for another video. For now, keep the moral. A group was never really about plastic and stickers. It is a pattern, and patterns are free to reincarnate. If you want to see what this shape's geometry actually computes, subscribe. You'll want to be here for that one.